All right, so we'll get started. And as I mentioned, to some degree, this is going to be review and setting our notation and conventions clear. So our first topic is the Schrodinger equation. So this Schrodinger equation is an equation that takes the following form. IH bar, partial derivative of this object called the wave function, that depends on x and t, is equal to minus h squared over 2m, second derivative with respect to x, plus v of x and t, psi of x and t. And that's a full equation. That's Schrodinger equation. Now, this is not the Schrodinger equation in most generality, but it's a Schrodinger equation for the case that you have a potential that depends on x and time. For the case that you're doing non-relativistic physics, because this thing, you may remember, is p squared over 2m, is the kinetic energy operator. So p squared over 2m is non-relativistic. That's a non-relativistic kinetic energy. So this is non-relativistic. Moreover, we have just one x here. That means it's a particle in one dimension. So we've done a few things, but this is general enough to illustrate our ideas. And the most important thing that should be said at this point is that psi of x and t, which is the wave function, belongs to the complex numbers. It's a complex number, and that's by necessity. If psi would be real, this quantity, the right-hand side, would be real. The potential is a real number. And the left-hand side, on the other hand, if psi is real, its derivative would be real, and this would be imaginary. So it's just impossible to get a solution of this equation if psi is real. So psi complex is really the fundamental thing that can be said about this wave function. Now, you've used complex numbers in physics all the time. And even in electromagnetism, you use complex numbers, but you use them really in an auxiliary way only. You didn't use them in an absolutely necessary way. So for example, in E&M, you had an electric field, for example, for a circularly polarized wave. And you would write it as this. Let me put a z here. E0. X hat plus y hat, those are unit vectors. I is a complex number, is the square root of -1, e to the I kz minus omega t. You typically wrote things like that, but in fact, you always meant real part. An electric field is a real quantity. And the Maxwell's equations are real equations. This is a circularly polarized wave, and this whole thing, by the time you take the real part of this, all these complex numbers play absolutely no role. It's just a neat way of writing a complicated electric field in which the x component and the y component are out of phase, and that you have a wave at the same time propagating in the z direction. So this, in here, E is real, and all i's are auxiliary. This is completely different from the case of the Schrodinger equation. This I there is fundamental. The psi is the dynamical variable, and it has to be complex. So we make a few remarks about this Schrodinger equation to get started. First remark is that it's a first order differential equation in time. This has implications. There's two derivatives, or maybe for some funny Hamiltonians you could have even more than two derivatives or more complicated things, but definitely there's just one derivative in time. So what this means is that if you know the wave function all over space, you can calculate what it's going to be a little time later. Because if you know it all over space, you can calculate this right-hand side and know what is the time derivative. And with the time derivative, you can figure it out what it's going to be later. A first-order differential equation in time is something that if you know the quantity at one time, the differential equation tells you what it's going to be later. So that's really sufficient psi of x, of all x's, at some time t naught determines psi at all times. Second property, fundamental property, the equation is linear. So if you have two solutions, you can form a third by superposing them, and you can superimpose them with complex coefficients. So if you have two solutions, psi1 and psi2, then A1 psi1 plus A2 psi2 is a solution. And here the A's belong to the complex numbers. So there, A1 and A2 are complex numbers. As far as complex numbers are concerned, the first thing you just need to know is definition of the length of a complex number. So if you have Z, a typical name people use for a complex number, having two components, A plus IB, where A and B are real, there is the definition of the complex conjugate, which is A minus IB. And there's the definition of the length of the complex number, which is square root of A squared plus B squared, which is the square root of Z times Z star. So that's for you complex numbers. So the property that makes this into a physical theory and goes beyond math is what you know is the interpretation of the wave function as a probability. So what do we construct? We construct a P of x and t, or sometimes called the rho of x and t as a density, and it's defined as psi star of xt. Now, here the notation means this psi star, we put the star here. It really means psi of x and t complex conjugated. You complex conjugate the wave function, and you get that. We put the star here, and typically don't put the parentheses unless you have to complex conjugate something that is a little ambiguous. So psi star of x and t times psi of x and t. And this is called the probability density. Probability density. And the interpretation is that if you take P of x and t and multiply by a little dx, This is the probability to find the particle in the interval val x comma x plus dx at time t. So this is our probability density. It's a way to make physics out of the wave function. It's a postulate. And the consequence of this postulate, since we're describing just one particle, is that we must have that the particle is somewhere. So if we add the probabilities, that the particle is somewhere all over space, this is the probability that the particle is in this little dx. We integrated, that must be equal to 1. And this must hold for all times. In terms of things to notice here, maybe one thing you can notice is the units of psi. The units of psi must be 1 over square root of length, because when we square it and we multiply by length, we get 1, which has no units. Key property of the Schrodinger equation. We will revisit the Schrodinger equation later and derive it sort of the way Dirac derives it in his textbook, as just a consequence of unitary time evolution. It will be a very neat derivation. It will give you a feeling that you really understood something deep about quantum mechanics. And it will be true, that feeling. But here, we're going to go the other way around, just simply ask the question. Suppose you have a wave function such that the integral of this quantity at some specific time is equal to 1. Will this integral be equal to 1 for all times, given that it is 1 at some given time? Now, you'll say, well, why do you ask that? I ask that because actually this could be a problem. We've said that if you know the wave function all over space at one time, it's determined everywhere. So any time later. Therefore, if I know the wave function at time equals 0 is good, time equal t0 is a good wave function, am I guaranteed that when I solve the Schrodinger equation, the wave function will be normalized well later? Yes, you are. And it's a simple or interesting exercise that we'll call it a quick calculation that I'll leave it for you to do. Which is show that ddt of this integral psi of x and t squared dx is equal to 0. So basically what this is saying, you got here 1, but think of this integral. I'm sorry, I'm missing a dx here. Think of this integral for all times. Now it could be a function of time, because you put an arbitrary time here. The integral might depend on time. So it's a good question to think of that integral as that may be a function of time and takes its derivative. If its derivative is 0 for all times, and at some time is equal to 1, it will be 1 forever. So you must show that this is true. Now this, I think you've done one way or another, several ways maybe in 804. But I ask you to do it again. So this is left for you as a way to warm up on the subject. And you will see actually that it's a little subtle. It's a little delicate, because how is it going to go? you're going to go in and take the derivative of psi star. You're going to take the derivative of psi, and you're going to use the Schrodinger equation. You're going to take the derivative of psi star, and you're going to use the complex conjugate of the Schrodinger equation. It's going to be a little messy, but then you're going to do integration by parts, and you're going to get 0, but only if you throw away the terms at infinity. And what gives you the right to throw them away? You will have to think. And the answer is that you will throw them away if the wave function goes to 0 at infinity, which must do it. The wave function must go to 0 at infinity, because if it didn't go to 0 at infinity, it went to a constant at infinity, it would pick up an unnormalizable thing here. So the wave function definitely has to go to 0 at infinity. But that will also not be quite enough if you're careful about what you're doing. You will have to demand that the derivative of the wave function doesn't blow up. It's not asking too much, but it's asking something. A function could go to 0, presumably, and its derivative at the same time blow up, but it would be a very pathological function. This will bring us to something that we said we're going to try to be precise, but it's not so easy to be precise. When you try to be precise, you can exaggerate and go precise to a point that you're paralyzed with fear with every equation. We don't want to get that far. We want you to notice what happens and just look at it and state what you need. Why can't we be precise? Because at the end of the day, this equation is extraordinarily complicated and maybe crazy if the potential is crazy enough. So functions, mathematicians can invent crazy functions. Things like a function that is 1 for every rational number and 0 for every irrational number. Put that for a potential here, and who knows what one gets. So we're going to take mild functions. We're not going to make them very complicated, and we're going to be stating very soon what we need. So what you need for this to work is that the function goes to 0 and the derivative goes to 0.